Okay, am I sharing? I hope I'm sharing. Alex, just let me know if we're sharing screen. All right, oopsie. Let's go into present mode. All right, so if you're here today, conceivably you're here because you want to learn how to make a knowledge graph with Neo4j, and I'm going to talk about a simple way to do this using some really basic machine learning. There's obviously much more in-depth, complicated ways that we can do this, but we're going to just start simple today. So my name is Claire Sullivan. I am a data science advocate at Neo4j. You can find me on Medium. I have a whole bunch of blog posts there about how to use Neo4j, and I post a lot in the forum towards data science, but you also might be interested, especially if you're just getting started your data science journey with Neo4j, you might be interested in one of the links that I have there. I have a video series. It's 5 minutes or less for each video on how to get started as a data scientist in Neo4j. It's called Bite-Sized Neo4j for Data Scientists. And of course, you can also find me on Twitter because everybody's on Twitter. So, okay. Knowledge graphs. All knowledge is controlled by Google, of course. Okay, that's not entirely true. Perhaps several of you have a lot of data that you want to put into a knowledge graph today as well. And so we'll talk about how to do that. But let's kick off, and we're going to do this in chat. Okay. In chat, let us know, when do you think the idea of a knowledge graph first got invented? When was the first instance that we know of or whatnot of knowledge graphs being discussed? So throw that in chat. Let me know what you think. Don't be shy. If you attended one of the earlier workshops this week, people were very comfortable in using chat. March 1971. Got 1980, mid-1900s, 2001. Okay, what is an knowledge graph? Don't worry, we're going to talk about that in a minute. Okay. 60s maybe, World War I, before 1800. Okay, so I'm going to go into the source of all knowledge, which is Wikipedia, despite what my slide here says. What I found there was 1972, that somebody came up with this idea of how to build modular instruction systems. But 1985 is a good answer also, because things really took off with this idea of WordNet, which was semantic relationships between words. Now, I love the other answers that are coming in here, and I'm totally going to be looking some of these up when we're done. So we are going to be using some code today. You don't have to code along, but if you want to do that, that's cool. There's a repository that has all of the code for today in it. It also has the slides. This is the repo. It is completely optional whether you use this. The code that we're going to run today, you don't even have to clone the repo for, but it's just if you want to run the code on your own later or whatnot, you can find it there. So speaking of that code, today we're going to be using Jupyter or Google Colab, some common notebook tools used in data science. I'm going to be demonstrating things in Colab. If you have Jupyter, you can run this yourself. You're going to want to manage some dependencies in the repository there in a requirements.txt file. If you you'll notice if you go to the repository that there's a Docker image there. The instructions on how to use the Docker image are within the README. We're not going to do it today. I did it in the previous nodes workshop. We're going to keep it a little more straightforward today. We'll be using the free Neo4j sandbox. Now, those of you who attended one of the workshops earlier this week learned how to use Aura. One of the things I'll tell you about Aura, there are free database instances there, but we're going to be using the Graph Data Science library. And in the free version of Aura, it doesn't exist there. So Sandbox has GDS built in, so that's why we're going to use Sandbox today. So if you populated an Aura database earlier this week, don't worry, it's all good. Okay, so machine learning. dump some data in, do some linear algebra, get some data out. And what if it's wrong? We just stir that pile. Okay, you're going to see that today. We will be stirring that pile today, but it's all good. So the GitHub repo link, we're going to post several times in the slides. I think I have 3 separate slides where we will post that link, but hopefully it'll show up in chat as well. There's the Nodes KG workshop repo link is in chat right now. Okay, by the end of this workshop, you will be able to apply data science and machine learning to a knowledge graph, which means that you will vectorize that knowledge graph. We'll talk about what that means in a bit. But first we have to create that knowledge graph, which means we have to get some relevant text and extract relevant information from it. Those first 2 bits of the chain here, we're going to use natural language processing for, NLP. And then the second half is graph data science and basic machine learning. Okay, if you take nothing else away from this course, I want you to remember these 2 things. First off, the first half of that pipeline being NLP, there is no proverbial silver bullet. NLP is an art unto itself. There are jobs that are specifically out there for NLP experts. And there's a reason for that, because NLP can be hard. I'm really glad, Manish, that you asked this question. Is it possible I can give an intro of why graph databases versus NoSQL versus RDBMS? Yes, let me just quickly answer that question. Graph databases treat relations between the nodes as a first-class entity, which means that we can do traversals much easier and much more efficiently than some sort of SQL thing or an RDBMS. So you'll get to see that here in a minute. 2 key concepts. Second concept. The quality of what you get out of a knowledge graph depends on the quality of what you put into it. Perhaps you're familiar with the acronym GIGO, garbage in, garbage out. We're going to be creating really small knowledge graphs today. And those of you who work with them know that knowledge graphs can get really detailed. So just keep that in mind, because the knowledge graphs that we're using are not super high quality. Okay, and by the size, we're talking about the number of node labels, the number of relationship labels. So just keep that at the back of your head. Okay, we got the question earlier. What is a knowledge graph? This is an example of a knowledge graph around the subject of the Mona Lisa. Okay, the Mona Lisa is this node in the center. The nodes are the circles. The relationships are the arrows. So for instance, we see the relationship that Mona Lisa is in the Louvre. Okay, the Louvre is a museum. Okay, and Da Vinci painted the Mona Lisa. These are facts that we kind of know. And the idea here is, how can we connect those bits of knowledge to each other? So then you'll notice down in the lower right, I've got this node called James. And I see that James is a person, and James likes the Mona Lisa, has lived in the Eiffel Tower, maybe not, maybe James has lived in Paris. Knowledge graphs are notoriously noisy. So obviously James has not lived in the Eiffel Tower, but that's something that we get to deal with as data scientists. Now, we see that Lily is a friend of James. We might think then that Lily, who does not presently have a relationship to the Mona Lisa, we might want to recommend that Lily go see the Mona Lisa, particularly as we see that she's also interested in Da Vinci. So we can use knowledge graphs not only to help us understand some corpus of information, but we can also use them to make stuff. Okay, so let's talk about a little bit more about that knowledge graph. Google famously said this thing about knowledge graph: things, not strings. Okay, so things are those nodes and relationships that you saw in the previous figure. Strings would be the raw text that we're sending in. Now, if I have a ton of raw text, it's not going to be something that I'm going to want to scroll through to get my answers. Speaking of answers, what knowledge graphs are useful for? You see that second sub-bullet there, question answering. Okay, I could say in my previous slide, where was the Mona Lisa, where's the Mona Lisa located? And you could see the Louvre. You could even go further and say that she's located in a museum. So I want to be able to query the knowledge graph quickly to get question answers back. I can also use it for search and recommendation engines. So let's talk quickly. Actually, we'll save that as an exercise for a minute. we can generate them in a lot of different ways, and I'll show you examples of each of these. We can have co-occurrence, which means two terms appear in the same document or close to each other in text. We can use these things called resource description frameworks, or RDFs, or we could use a subject, verb, object triple, and I'll show examples of all these here in a minute. Word co-occurrence. This is an example of a whole huge corpus of peer-reviewed research articles. And what they're doing is they're looking at which words are most popular. Those are seen as the large nodes, such as coronavirus infection and pandemic. And then they're all connected to each other based on coronavirus was perhaps connected to pandemic. Those two words occurred a lot in articles with each other. And we see the colors indicate groupings of topics. So for instance, on the top, we have yellow, and we can see female, male, adult, middle-aged. So we see some things like which organs are associated here. I don't expect you to be able to read all of this, but this just kind of gives you an idea of word co-occurrence. So I've been asked to also share the slides. The slides are in the repo, so you can find them there. Okay. RDF triples, resource description framework. This is a kind of a standard that was put out by the World Wide Web Consortium. And what it looks at is just links that are possible on the web. You can see I've got things like titles, doctor, I've got names, I've got emails, web pages. This is something that we do treat within Neo4j. If you look up neo-semantics or N10s, you can use those here. But we're gonna do something different today. We're gonna be doing natural language processing. So for instance, we're gonna be creating these subject, verb, object triples. So think about Da Vinci painted Mona Lisa. In this case, and by the way, I apologize, this is very English centric. To do this in other languages than English, you will have subjects and verbs and objects. But when we do this, we're going to be using the grammatical structure of English to detect these things. So you'll want to look up what the equivalent thing would be in your native language. So again, Da Vinci would be our subject. Verb is painted. Object is Mona Lisa. So we're going to call these SVO triples. And I'll show you a way to extract these in a bit. Okay. When we do NLP, there's a whole bunch of ways to do NLP, and this is why NLP experts are really valuable in this process. So we start with named entity recognition. We want to find things in our text like Da Vinci and Mona Lisa. And there's tools out there to do that, which we will be discussing shortly. There is a way to add additional properties to this verb in SVOs. While extracting the data. We're not going to get hugely into that today. That's a lot of more in-depth NLP, but we will be making these nodes a little bit more interesting than other than just SVOs. You also might hear them as SPOs, where P stands for predicate. But I'm going to warn you right now, as we do this, verbs are really difficult to reliably detect. And you're going to see that at work here. Again, very language dependent and very topic area dependent. If we were doing, that previous toy example of the Mona Lisa, those are pretty easy things. But think about if you were dealing with some serious scientific topics, NLP engines might not always detect like the named entities. So you're going to need a special vocabulary for those things. This is when it's great to have a subject matter expert involved. Those subject matter experts can tell you what the right named entities are and what the right verbs are. So they're really important in this process. Okay. This here, I don't expect you to be able to read this. This font probably looks really small on your end. But what I did was I just took the first paragraph of the Wikipedia entry for Barack Obama, and I used a tool called Spacey. Spacey is a Python tool for doing, it's really simple, it's for doing NLP, and it's particularly good at named entity recognition. So what you see here are the named entities associated with Barack Obama. So you can see they're colored, so people are kind of in this purple color. dates are in kind of a light green. I've got organizations or regions, geopolitical regions. I've got all kinds of stuff here. And we're going to use this stuff. We're going to use all of this stuff, in fact, to populate our knowledge graph. But we're going to talk a little bit of vocab here on how this is actually going to work. One thing, I could also represent this instead of looking at this in kind of this image format. I could also represent this in this kind of arrows format here, zooming in. And this is kind of fun if you're kind of getting more into NLP and graphs. What we see here is arrows that indicate nouns pointing at other things. So I'm getting a lot of blank screen and no audio, Alex. So I'm just kind of trying to reach out. Those of you in chat, can you tell me, are we getting sound through? Okay. Some connection problems. Okay, they say it's back. I'm back now. Those of you who say that we were having these problems, please let me know in chat if we were having sound. Loud and clear now. Okay, cool. Apologize for that. Can we go back one slide? Absolutely, we can go back one slide. So let's, oops, that was forward. Okay, so here is going back. The audio keeps dropping in and out because you start from the NER slide. Okay, so here we are. This is the named entity recognition slide. And again, what we're looking at here is just raw text, and the colors are the different named entities that Spacy found, Spacy being a nice NLP package in Python. So the colors here indicate the type of entity that Spacy found, such as person or date. So yeah, another way we can represent that is through these arrows here. So I've got nouns that point at verbs. I've got compounds. I've got subjects. It's pretty complicated stuff. Let's look at this instead, a little easier to view. I took just that first sentence there. Barack Hussein Obama II is an American politician, ... So what I'm going to look at is a few different columns here. Every row here represents one word. So for instance, I've got, let's look at is. Okay, is a verb. We have this thing called a lemma, which is the base of that verb. So is a form of to be or be. Then we have tags, we have parts of speech and dependencies. And then I have this thing called is stop. There are stop words in NLP, and these are the words that just kind of don't really matter, such as the. I have punctuation, like the period at the end of the sentence. Those things are not useful when we're talking about assembling the knowledge graph, so we'll be getting rid of those. You'll notice that I have this thing called the root of the sentence. And probably, you know, it's important because I highlighted in big, bold, red face. The root is that most important verb in the sentence. That's the thing that everything takes off from. So it's going to be important for us to detect the root. Also, we have this thing called a compound. We're going to be looking for those subjects that belong to the root. Spacy detected that the Roman numeral 2 was the subject, but that the compounds Barack Hussein Obama related to that subject. So in named entity recognition, Spacy will lump all of those things together. Here's another one where I have an object, okay, and then I have a compound word in front of that object. Again, Spacy should identify that as being one named entity. Okay, let's talk a little bit about the packages that we'll use today. And we're going to go through, by the way, I didn't say this earlier, we're going to be going through the lecture portion, and then in the second half, we'll be getting to coding here. So the packages that we're going to be using today, we're going to be using Spacy, like I've already discussed. We're going to be scraping Wikipedia. And there's a Python package for doing that. And we're also going to hit the Google Knowledge Graph. I said earlier, Google is the source of all knowledge. We're going to take advantage of that. And that's going to be in the first half of the demonstrations. The second half, we're going to use Wikidata. And you can use a bot for scraping that. PyWikibot is what is going to be in this code. And then we're going to use some common libraries within Neo4j. First off, the awesome procedures on Cipher or APOC. APOC, if you can't find anything within Cipher within Cipher to solve a problem, chances are it's already in APOC. So APOC is a great place to look when you're stuck. We're going to be using Graph Data Science Library, as I mentioned, GDS, and then of course Cipher. I don't expect you to actually know how to use any of these things. We're going to demonstrate that and get to use it ourselves. Okay. One thing I forgot to mention is just a question for y'all. We've got these verbs and objects and subjects, and question for you is, how might we get the correct verb associated with each subject and object? And this is something you can put in chat. And I'll point out, for instance, that I have two verbs here. I have be, that's the lemma of the verb is, and then I have serve, which is the lemma of the word served, past tense of serve. So I have objects here and subjects here. Somebody throw out in chat how you think I might put the correct verb with the correct noun. So let's just take a minute to chat in on that. No wrong answers? What do y'all think? I'll give you a hint. There's a lot of ways. Limitize it based on the part of speech tag, I think. Okay. Within a certain number of words. Ah, that's interesting, because language is so messy that we can't assume that there's a certain number of words here. Okay, verb present between two objects. That's yes, absolutely. But I have two verbs here. Use NLTK. That's NLTK, for those of you who don't know, is a different Python package for doing what we're going to be doing today with Spacey. Order verb after noun, key value dictionary, co-occurrence, dependency parsers. Yes, I'll tell you that these are all things that could be helpful. We're going to be doing something kind of cheesy, admittedly. We're going to be looking for the verb that's closest to the noun. So in this case, be is closest to Barack Hussein Obama II, and serve is closest to our object of United States. Any software for syntax trees? Oh, that is a can of worms right there. That, yes, but it's pretty hard to do and varying quality. So, LSTMs to learn the sequence of sentences. That is a very advanced one. I love it. And that's not going to be what we use today, but this is kind of an art going into these sequences of sentences. You could look at transformers to do these things. Those of you who are more experienced in data science and machine learning will know what I'm referring to. Those of you who aren't totally cool, don't worry about it. Okay, so here's my second mention of the GitHub repository. This has been posted in chat a few times. Again, it is optional. We will not need it for today. It's just if you want to have the code yourself, you want to be able to reference back to it, you want to be able to run it on your own machine. It's all good. Okay, link prediction. Oh yeah, we're going to be talking about that for sure. Okay, we are going to use two methods today, two different methods. I'm going to talk about method 1 and method 2. Method 1 is what I call the NLP only approach. So we're going to use strict NLP to discover those subject verb object triples. Let's talk about how we're going to do this. This is the code you're going to see. It's just a flow chart of the code you're going to see. We're going to start with cleaning the text. So we're going to get some base text here. Completely, we haven't done anything to it. We're just going to scrape it, and we have to clean it. Those of you who are working data scientists know that 80% of the job of a data scientist is what I call data janitor. So the janitors are going to clean and clean and clean, and we're going to be doing a bunch of it today because, like I said, NLP is dirty. So once we clean the text, we're going to get all of those named entities, and we're going to get the subject verb objects for each of those entities. We could, as one of you identified, we could put adjectives in here as properties for our subjects and objects, even our verbs if we did it right. We're not going to do that today, optional, but yeah, that's totally legit. And then we'll assemble our graph. Now, this has a few advantages, which is over what I'm going to talk about in method 2. One of the advantages, one of the key advantages here is that we have limitless verbs. If we can find the verb in the sentence, we're good to go. We can have a relationship that is that verb. The drawback here, because this is a messy process, is entity disambiguation. So you can think about text that might be involved with Barack Obama. Now, I just said Barack Obama, but our previous text said Barack Hussein Obama II. We could also imagine that text might say just Obama. Those are all three the same thing, but with the NLP only approach, the named entity resolution might not get that. So that's something we have to think about, and I'll show you some ways of some strategies of doing that here in the actual hands-on. One of the things that is common to machine learning, which we will be doing some of shortly, we have columnar data, okay? Our columns could represent first word, second word, third word. Just think of it that way. Everything that we do in machine learning involves turn a thing into a number and then do something with it. But words aren't numbers, okay? So what do? Well, there's all kinds of strategies here. And fortunately, some of them are built into Spatie. One of the most common ones is called word to vec, where we convert words into vectors. And it works on this thing called a skip-gram approach, where we're going to go through a sentence and we're going to skip one word, and then we're going to go and move our window and skip the next word and skip the next word and see which words are in like a library here, a library of words. And I'll tell you what library we're going to use here in a minute. So if all of these words appear within our corpus, we can assign numbers, like maybe number 1 corresponds to Obama, and the number 5 corresponds to states. So this is just a process that we use for turning words into numbers. We call these things vectors when we get a whole list of them, or embeddings, same thing. And what we assume here is that similar words will be close in vector space of those embeddings to other words. So for instance, you see on the right, Boston is close to Seattle, because they're both cities. Research is close to science. And we have ways mathematically that we can determine how close those things are. Okay, let's go back into a little bit of our workflow here of specifically what we're going to do in method 1. First, we're going to get that Wikipedia entry for our starting search term. And I'm going to do Barack Obama today, just so you know, so we keep it consistent, but you can put in anything here. We're going to do natural language processing on this text to get our SVO triples, which we will add to the graph. Then we're going to update node labels and properties. I'll show you what that means in a minute. We're going to deduplicate our SVO triples. We're going to clean. We're going to dedupe some more, clean some more. That's the data janitor part. And then we create some what we call in-memory graphs. This is a GDS term that you'll find out a bit and see. That we're going to create graph embeddings. There's the word embedding. We're going to be using the graph to create an embedding, not words. And then those embeddings are going to be used to do some machine learning. Okay, the NLP part. Paolo just said the vector spaces depend on context. That's absolutely true, they can. And this is where I was referencing like scientific literature. That's going to create a totally different vector space than, say, political literature. So the choice of vocabulary that you use is pretty important. The NLP portion is just a whole bunch of cleaning. We get rid of control characters. We're just going to do some light cleaning. We create a document in Spatie. Don't worry about this stuff. This is just how we are assembling our SVO triples, and I'll show you that at work here in a minute. Okay, once we have the SVO triples, we're going to make them a little more sophisticated by querying the Google Knowledge Graph. And the Google Knowledge Graph is something that you can get an API for, and you can do, I think it's 100,000 requests to 100,000 API hits to that thing per day for free. You don't have to set this up today. If you want to run the complete code on your own, you'll want to do that. You can just Google search, Google Knowledge Graph API, and you'll be able to figure out how to do that. Again, these slides are in the repository, so that web link up there will be in those slides. Okay, let's say we do that. Here I am querying the Google Knowledge Graph for Taylor Swift, and I will tell you, I personally know just about absolutely nothing about Taylor Swift. Okay, this is what it's going to give back when you do this. First off, I have a name here. My name is Taylor Swift. I see that Taylor Swift has a few different types. Taylor Swift could be a thing, or Taylor Swift could be a person. Now, that's kind of interesting because that could give us our node labels. And Taylor Swift could have multiple node labels, and in Neo4j, that's totally legit. Then I have this description of Taylor Swift, which is, a sentence or two about who she is. And in fact, I could have multiple descriptions, and that's a little problematic. We're just going to use the first description today, but you could use all of them if you want. And then I've got a URL associated with Taylor Swift. Now, these things that I've highlighted here, we're actually going to use as node properties, just to make our graph more interesting. And then the other thing I should tell you is that not all Google Knowledge Graph entries have all of these things populated. So that's something we're going to have to deal with as we go along here. Okay, now again, we're going to use these things to add to our graph. We're going to add node properties. So you see here that my objects are going to get 4 properties associated with them: name, node labels, description, and URL. But then you see this thing, word vec. Okay, Spacey, we're going to use Spacey to generate word vectors using that word to vec approach. And in this case, just for today, I've generated 300-dimensional word vectors. That 300 is a totally arbitrary number, but we're going to be using those word vectors a little later to compare the results of our ML to the graph vectors. That's why I'm including those there, is just so they're handy. When we do that for the Barack Obama graph, this is what it's going to look like. Don't worry about reading that. We're going to start with about 862 nodes, 832 relationships. That's just what it's going to look like. We're going to make that ourselves here shortly. Okay, I mentioned that we're going to do 2 methods here. I'm going to call method 2 the NLP Lite approach. We're going to do some NLP, but then we're going to get a little more sophisticated. To do this, we're going to be using Wikidata. Now, if you look at Wikidata, like this is the entry for Douglas Adams. All of the examples always use Douglas Adams as their demonstration. I can see here that I have an identifier for Douglas Adams, a unique identifier. That's called the Q code. So Douglas Adams here is Q42. If you know who he is, that's actually kind of cute. And the label Douglas Adams. And then I have these things called P codes, or properties, that you see in purple there. So I see that this property is educated at. Okay, this is starting to give us some hints here. And then I've got these qualifiers, or the values. Sorry, I want to go with the values here, the orange thing. So educated at St. John's College. So hang on a second here. I've got Douglas Adams, educated at St. John's College. I've just assembled my triple right there. That's pretty cool. That's nice and efficient. And I don't have to do anywhere near the NLP cleaning. I don't have to do this verb to noun attribution. This is a really nice, convenient way to do it. So we start with a little bit of text cleaning. Get rid of punctuation and stuff like that. Pretty basic, pretty minor stuff. And then we're going to get all the named entities, just as we did before, but then we're going to take all of those named entities and we're going to get the claims for them. So that's each of these properties with their values. And we're going to obtain Wikidata for each of these claims, for each entity. So that's taking the claim of educated at and getting the value, and then we're going to assemble the graph. Okay, I really like this approach. It's much simpler and much cleaner. Also, it has the advantage of entity disambiguation. If I were to search for Barack Hussein Obama II, Wikidata is going to give me just one entry back, which is super useful. But the drawback, as you're going to discover here, is that we actually have to provide the list of verbs, or P codes. I mentioned that there's the Q code, which is the unique identifier for Douglas Adams. P codes are the properties or the verbs. So I would have to specify, there's going to be a number associated with educated at. I don't remember what the number is off the top of my head, but let's say it's P28. So I would have to specify that I'm interested in the P28 properties of Q42. So I have to specify the verbs. That's a drawback here. Okay. When we do this, we're not actually going to run this. I'm going to provide you with a pre-populated graph because it can actually take a little bit to run. But we build a bot on to do this scraping here. And this web page will tell you how to create a token for that bot. These bots are pretty sophisticated. You can add things to, you can add content to Wikidata with these bots. This is just, we're scraping Wikidata with them. If you want to get into it, this is how you would do it to create that token. Again, the slides are provided in the repository that will show you specifically how to do this. Okay, so once we do this, we're going to create a graph, and this is what the schema is going to look like. I have a subject and an object. My subject and objects have Q codes associated with them. They have labels, and then they have this type, is instance of. Let's see. Is instance of is actually a P code. I happen to know off the top of my head that it's P31. So I would see that Douglas Adams is an instance of a human. The university would be an instance of university or college. And then I have the claim, which is my verb, and that's by the P code. So P code is instance of. Okay. When we're going to do this again for Barack Obama, and this graph is what you're going to get on the other end. Again, I don't expect you to read that. That's just to give you some visual familiarity with it. Okay, so let's talk about then how we're going to use all of this in machine learning. After this section, we're diving in. We're doing some code. Thank God. Okay, so machine learning on graphs. Why would we do this? I like to give this example. You see the mailbox in the corner. We talked about making recommendation engines. I live in a fairly rural area in the mountains. There is a big hardware store near me. I built the house. Well, I didn't personally build, but I had somebody build my house. And so we'd go to that hardware store with some regularity. Now, my hardware store could say, okay, Claire's buying a lot of wood and nails, a lot of wood. So we think Claire's building a house. Because houses, we could have a relationship between house requires nails, requires wood. Okay. As time passes, and let's not talk about time-dependent graphs because that's a whole can of worms. But as time passes, Claire starts buying things like paint and lighting fixtures and drywall. So Claire's getting a little further along in this build process. So we might think that once Claire is done, she might want to put a mailbox at her property. Okay, and then we're going to recommend to Claire a mailbox. Well, if you did this actually for me, what you would find out is that I didn't buy a mailbox. Well, why? Well, it turns out we have no mail service here where I live. Now, let's say that we'd actually looked at my geo neighbors, the people who live in my subdivision, and we realized they didn't buy mailboxes either. The question earlier about RDBMSs versus graph databases. Here's another reason why you'd want to use a graph database. In an RDBMS, we talk about each data point being independent of each other. So when we develop models, think of a spreadsheet, think of a pandas data frame. Each row we assume to be independent of another row. And that's the basis of our machine learning model. However, what that did was that ignored the fact that we know there's a connection here. We know that I'm connected to each of my neighbors in my subdivision here. And so our knowledge was incomplete because we didn't see that connection. We didn't see the linkage between me and my neighbors here. And had we done that, we would have had a much more accurate recommendation engine by considering that our data is linked. So like I said, graph databases treat relationships as a first-class citizen. the models can include the same data as our traditional machine learning set where we have independent rows, but now we have another vector that takes into account those relationships. And you'll see in a minute that that's really powerful. Okay, I mentioned word2vec earlier. Word2vec typically creates one vector per word, and Spatie is creating a vector based on a sentence, and then it's averaging the word vectors across those sentences. Just details we don't need to worry about right now. Suffice it to say, word vector, throw text in, get vectors out. Vector, one vector per named per description for our subjects and objects, as you're going to find out. Okay, turns out that there is a similar embedding approach called Node2Vec. Very similar to Word2Vec. It's going to be kind of a skipgram approach, but what's going to happen here is slightly different. Let's say we have that starting node V in the center there. Okay, now what is V? How are we going to vectorize V? When we use Node2Vec or Word2Vec, we had sequential things, like a sentence has a sequence of words in it. And graphs don't. What's a sequence in a graph? They just kind of bounce all over the place. But bounce all over the place is different than, it's going to give us a hint here. So what we're going to be doing is actually a random walk around the graph. So V is connected to certain nodes here, like X1 and X2. And I have weights between those nodes, these alpha parameters. And you see that those alpha parameters are determined by values called P and Q. What P stands for is the return parameter. So if I jump from V to T, for instance, what's the probability that I jump back from T to V? Okay, that's my return parameter. In GPS, you'll hear it referred to as return factor. And then Q is my walk away parameter. So Q, let's say I go from V to X2. Alpha in this case is what's my probability of moving away from V. Now, those of you who work a lot in software, you might recognize that this is like breadth first search and depth first search. Higher P values mean I'm going to stay local, and higher Q values mean that I'm, or lower values of Q mean I'm going away. So breadth first search and depth first search, that's bread and butter for software interviews. So you can talk, if you want to get really sophisticated, you could talk about how you could do those searches within a graph. So there's some hints for your upcoming interviews. Okay, when we run Node2Vec, what we're going to wind up with is an embedding, and this is a really small font. We're going to create these here in a minute. I just created them quickly for some nodes in one of those two graphs. I don't even remember which one anymore. But again, I have a list of floats, so normalized values that are generated by just hopping around the graph a few times. So that's potentially going to be handy. Now here I show an embedding dimension of 10. I've got word vectors that are going to be 300, whatever. It's all good. We can do things with these vectors like we could do with just normal word vectors, where I could do node similarity. I could do a cosine distance between two vectors. This is just showing it for the words, but yeah, so all the math that you could do with a word and vector, you can also do with a graph embedding. Okay, we can also do things like our traditional TSNE plots. So this is the T-distributed stochastic neighbor embedding. So what we're doing is we're actually taking our big embeddings and we're doing dimensionality reduction to two-dimensional space. And here I'm just showing some simple little binary classification. I've got a 0, I've got a 1. Ideally, what we would see is all the red nodes would group together and all the kind of teal nodes would group together. But all of those same ML techniques for traditional vectors are available to you on graph vectors. Okay, phew, we're going to get this party started now. I'm going to propose that we take like a 3-minute break here. Everybody get up, stretch. We've been going at this for 50 minutes or so. So take 3 minutes, and we're going to be transitioning into Collab, Google Collab. We're going to transition into Sandbox, and I'm going to show you some GitHub code. So take just a minute here, give a stretch, and we'll be right back. repo. For those of you who are still at your screens, you might want to pull up this GitHub repo on your web browser because we'll actually walk through a little bit of what's in here. Don't know if you can hear my dog in the background. Yeah, my dog is a rescue. She's just turned 5. She's great. Okay, I'm going to just throw the link to this repo in the chat again. All right, let's start back in now. This, like I said, this is the repository. You don't have to clone it right now. But I want to just kind of walk through just quickly what's here. There are 4 or 5 directories that you're probably going to care about. I don't know why there's a data directory and a JSON files directory, but I'll fix that. A couple that you're going to want to look at. First, all of our slides here that we're going to be going through, they're all right here. So I have some slides that we're going to walk through, these are just HTML slides that are created from the Jupyter notebooks. And then I'm going to be updating this repository here after the workshop is done. There'll be a new file in here that is the PDF of today's slides. So then the notes themselves. Okay, so I've got, I have 5 notebooks here, run all of these today, but we'll go through a few of them. And then, let's see, I have all of the Cipher queries. Now, this is probably going to be something that you want to use today. All of the Cipher queries today are in the Cipher Queries directory. In particular, I want to just call out this starting queries thing. I have a few general queries that are going to be helpful. If you want to view the whole graph, we're going to look at line 8 here, match n, return n. I'll talk about what that means in a second. We can delete everything in our graph using here, and then we can look at, this is another great function, :history, see what you've done in the past. And then here's how we're going to be importing our data files into our graphs. So that's all available in the repository. There's also a pretty extensive README here. Okay, so one of the things I'm going to tell you, which is going to appear after we're done with today's workshop, I'm going to be asking you questions during this. There will be a file that appears here that's the answers to these questions. I don't want to put it in here because I don't want any spoilers, but you'll be able to find that later. Okay, so what we're going to do first here is we're going to go to Sandbox. Okay, those of you who are not familiar with Sandbox, these are free Neo4j instances that you can create. They last for about 3 days, and then you can extend them for, I think, 8 more days if you want to. But you can just spin up whatever you want. So to do that, I'm going to click on this button here, New Project, and I'm going to create a blank sandbox. Okay, so let's go ahead and just launch this. And what it's going to do, it's going to create that sandbox instance for me. Okay, cool. Let's look at some information in here that we're going to need. Okay, here, by the way, just in case you're curious, this terminate button makes it go away. Connection details. Now, these are the things you're going to want to know. For instance, each sandbox has its own IP address. It's using the Bolt protocol, and we're going to need that to make our connection. We're going to have a username. It's always going to be Neo4j for a sandbox. And then we have a password. So we're going to want this stuff here in a minute. Okay, so we've got our sandbox. We've looked at the repo. Let's actually get started now with some code. Okay, so I'm going to, like I said, create Collab notebooks to do this today. Again, you can do this in Jupyter if you want. And I just create a subdirectory for these things. Here's how we create a Collab notebook. So I'm going to click on the button new. It's going to show up in my list. I'll click more. And you can see, whoopsie, you can see second from the bottom is Google Collaboratory. Okay, so we're just going to click on that. And it's created me a notebook. Cool. Let's, maybe, if that's too small for you to read, somebody dump that in chat and I can make that bigger. I just want to acknowledge something Pierre Emmanuel said. Let's see, the English Core Web MD has to be installed after the requirements. We're going to show how to do this here in a minute. But for those of you using Jupyter on your own machine, you will have to install that. I will show you how to do it. That's our vocabulary, the vocabulary of words that we're going to be using in Spacey here. But I'll show you how to do that in a minute. Now, we're going to actually pull in one of the notebooks from GitHub. So what I want you to do is click this thing, Open Notebook. Okay. Now, if you see this second one to the right here is GitHub. Okay. So what we're going to do is we're going to enter the GitHub URL. So GitHub, let's .com CJ 2001. Can't type today. And then our repo is called nodes 2001 kg. Actually, I could have just copied and pasted this over. Okay, so we'll give a search for that. And you can see here that it comes up with my 5 notebooks. Okay, we're going to actually, we're going to be using notebook number 2 here, but I'm going to run through some slides about what notebooks 0 and 1 do. Okay, so should have opened these beforehand, but here's my repo. So y'all can, okay. So we're going to get started here with method 1. Now, first thing, obviously, we're importing our packages. For those of you who want to do this yourself, I will tell you that Spacey came out with a new major version earlier this year, version 3. We want to be using version 3. It's just way better than version 2. Okay, now, in the mention about installing the vocabulary, here's how you're going to do it. We're going to be using Python 3 because, Python 2 is dead. Move to Python 3 if you're on Python 2. There's this command here, Python 3-m Spacey download. English Core Web MD stands for medium. Now, medium, there's small and large as well. If you download large, it obviously takes longer. This is the size of the vocabulary that we're going to be using. This is scraped off of the web, and medium is just a nice medium size. If you get small, though, the thing that's going to be different about small is that it does not do full-on word vectors, and we're going to want those today. So you're going to want medium at a minimum to do that. Again, there's the API key for Google Knowledge Graph. If you want to grab that, great. Again, not required for today. And then the next thing that we're going to do, and this is what you're seeing in those notebooks 00 and 01. We're going to tell Spacey to create a list of the tags that we would consider subjects, verbs, and objects. as well as the entity labels that we care about. So I've just kind of manually gone through and grabbed some labels that we're going to find of use to us, as well as which things we're calling subjects, which things we're calling objects, and which things we're calling verbs. And then we're going to spacey load our vocabulary here. We're going to create a pipeline. This is a spacey thing where I'm going to do this thing called merge noun chunks. For those of you who are interested, this is where the named entity recognition comes in. If you don't add this, what you would wind up with is separate verbs that are, or separate words that are Barack, Hussein, Obama, the second. So this is the thing that merges all of those via named entity recognition. Okay. We're going to query the Google Knowledge Graph. And, you know, I'm not going to spend too much time going through this stuff. These functions exist within the notebooks on how to do it. You can go through this code if you want, but essentially this is the thing that's going through, hitting Google, grabbing the name, the types, the descriptions, and the URLs. Okay. And then there's a bunch of helper functions. And what these things are doing is that, like I said, text is dirty. We have a lot of cleaning to do. And just these are functions that are going to help us clean the data. The ultimate goal here, the function that you care most about, is this create SVO triples function. This is the thing that after all of the cleaning finds the named entities, figures out which ones are subjects, which ones are objects, and then finds the closest verb to each of those things. So that's how we create our SVO triples. This is just what those functions look like. You can look at them in the notebooks. Okay, so what we do in this notebook, we're going to hit Wikipedia just to grab a page of text. You could throw in any text here you want, really. And I do want to say, by the way, that this is just one way that you can do it. There's practically infinite ways that you could assemble these triples. And I encourage you, if this is something you're interested, go try them. Okay, I'm not saying that mine is the best way. This is just a way. So do experiment with this on your own if you want to super get involved. Okay, so scraping Wikipedia. I have a few more functions here. These are what's going to get node labels. Node labels are going to be really important. Those are the things that are the type in Wikipedia. So remember, Taylor Swift was type person and type thing. Okay, we're going to use those. We're getting descriptions, we're getting URLs. That's all shown in code that you can look at, because don't worry about these things right now. I'm going to give you the graph that this assembles. We're going to run this step by step. You'll see this if you run through the notebooks 00 and 01. Here's what the triples actually look like. You'll notice that it grabbed the phonetic spelling of Obama, just one of those things. I grabbed the verb be. So Obama be American president, 44th president, Obama be United States. Okay, that's kind of weird. Again, this is one of the things that makes NLP hard. Let's see. Okay, we just got a bunch of cleaning here. This is what it will eventually look like. Now you'll see the first tuple in this list, it grabbed that Obama was a thing. Okay, the second one got really no node labels, no URLs, no descriptions. The third tuple here, though, kind of shows what the whole kit and caboodle looks like. So I've got 4 different node labels that we could use here for the United States is what these are attributed to. These are attributed to the objects. So the United States is a thing, a country, a place, an administrative area. All that kind of makes sense. And then I have my description here. Okay, now what I am going to do is I am going to take that description, the United States of America, commonly known as the United States, ... We're going to create word vectors around that sentence. So I'm going to have one 300-dimensional word vector that's associated with the object United States. Okay, so that's what's happening here. Okay, we're going to create the node list and edge list to populate the graph. We have helper functions to do it. Dedupe, 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 clean, dedupe. We do that a lot. And then this Py2Neo thing. This Py2Neo is a community driver for using Python to connect to Neo4j. Developed by Nigel Small. Great, simple, we love it. I will show another driver in some of these notebooks as well. I'll show the official Neo4j Python driver, and just to give you experience with both of them. if you're interested, go check out my Medium posts. I walk through examples on how to use these things in there. And then I have in 3 and 4 here, we're going to add our nodes and we add our relationships or edges to the graph as separate functions. The details of this, long and complicated. Let's not worry about it right now. Okay, let's see. Create some lists of tuples representing nodes and edge lists. This is just the mechanics of how this works. If you're super interested, I recommend that you go through those notebooks. So we create node lists and we populate the graph. One of the things that we will discover is entity disambiguation. We're going to do that. Don't worry about it. Here's the kicker, though. Let's say we are subject matter experts in this field. And this is one of the reasons, this is a demonstration on why subject matter experts are important. Let's look at in the graph, what you will find is that we do not have Michelle Obama in the graph because she wasn't referenced in that original line of text. So as a subject matter expert, we will have to add her in because we know that she's going to be relevant to the graph. So this is when you want to get them really engaged. What's missing in my graph? And that's actually what's in notebook number 1. Notebook number 0 is just assembling what we've talked about here. Notebook number 1 is going to show adding her back in. Okay. Okay. Oh, that's me showing what that problem is. Just a little bit of Cipher here. What we're seeing, match, if you're familiar with SQL, match is select in SQL. So we're going to match some node. Now, nodes are always shown with round parentheses, and relationships, as you'll see in a minute, are shown with square parentheses. So it's kind of cute. It's ASCII art. So remember, nodes were circles in our graph. Relationships were arrows. We're going to be able to draw arrows to show directionality within our graph. You know, we have where functions, very similar to SQL. So where this property name is associated with the variable n. So n.name contains Michelle. And we're going to return that node. So if you think about it, it does kind of look similar to SQL. So we're not going to worry too much here. All right, let me just pull up one other bit of slide, and then we're going to get going with that, the Collab notebook. Okay, so we're going to cut to the chase here. We're establishing our connection via Pi to Neo to our graph. You'll see this in a minute. We're assembling text based on both Barack Obama and Michelle Obama. We're assembling our node lists and our edge lists, and we're adding them to the graph. That's all that's happening in 0.1. And what we'll do here is we will load in a JSON file in a minute that takes the output of that. I've created a JSON that just takes the whole graph and we'll pre-populate it into our sandbox. Okay, so let's get started with that. Let's actually come into Sandbox. Okay, and we're going to click Open. Now what this does is it brings up the Neo4j browser. If you get some error here, sometimes right when you create an instance, you're going to get like a 404 error. It just means the instance isn't quite ready. Give it a minute or two and it will fire up. So just, you know, reload in a minute or two. Okay, now while it's coming up, I want you to look at the repository. Okay, we're going to go into Cipher Queries. And let's go into starting queries in the Cipher Queries. We're going to come all the way down to line 22. What we're going to do here is we're going to use APOC. APOC has this really nice function built in that imports JSON. And this is the web link to the JSON. You'll notice GitHub user content means I'm actually grabbing the raw stuff. If you were to use just the repository link, then you're not actually going to get true JSON. Okay, so I'm going to copy that line and I'm going to paste it in here. Okay, and let's just run that. To run that, we click this little arrow here, run, or you could hit Control Enter. This is going to take a minute. And I will tell you sometimes, depending on, you know, web traffic and whatnot, it's going to give you an error saying a timeout or something like that. Just try rerunning it again. Or if it really becomes a problem, One trick that we have here is I could create a different type of sandbox. I'm going to scroll down here, and I'm going to look for this thing called blank sandbox graph data science. Okay, we're going to launch one of these in a minute, but I don't want to confuse things. That one has a longer timeout on it. It's just, one little trick that we can do here. Are we done yet? We're not done yet. I'm going to click on the database icon here, and we'll see the graph actually populating. So you see it brought in 862 nodes. It's still bringing in data. This number will go up as it does. Okay, yeah, there's my timeout. Okay, but just because I happen to have worked with this graph before, I can tell you this is the correct number of relationships, 823. Let's just look and make sure that this looks correct. So I'm going to, if I want to see this graph, I'm going to go match node. Okay, so any node. I'm just calling that node N. Neo4j knows that it's a node because it's got the round thing on it, and I'm going to return N. Let's run that. Okay, and what this is going to do is it's going to create a visualization of my graph, and that's super cool. Okay, so here's my visualization. I see that I've got nodes and relationships. I personally, because I've worked with this graph before, know that this looks correct. If you were dealing with a new graph of yours, you'd certainly want to get into that. Now, here's a pro tip. These visualizations can take up a bit of memory, so we're going to close them when we're done, just so we're not using too much memory. Okay, so yeah, we've got now a graph. Now, we're going to go into the file. Now that we've populated this, let's go into Cipher Queries, and we're going to do method 1 queries. Okay, so we've already looked at the graph. Now, let's look at a specific node in the graph. I'm going to go match N, a node. I'm going to return that node, and I'm going to limit it to one node. Okay, this is very similar to SQL. You could just look at one line in SQL if you want. I'm going to represent this as a table. Now, I see that I have a label of node. I have node labels here. I have a list here. And in this case, I said that Barack Obama was the subject, but I have other node labels as well. I can see that that node has a name, has no description because I didn't grab the Wikidata for him. I can see that I have my 300-dimensional word vector if I scroll down enough. Okay, I don't have a URL for him. So this thing called node labels, so we're going to use this to create more node labels because you'll find that other nodes within the graph have some pretty populated ones. So going back to our repo, update node labels based on type ls list. Okay, it's actually, that should say on node labels list. Okay, so let's just copy lines 12 through 15 over into our browser. Okay, so again, we're going to create labels based on whatever's in this list here. I'm going to run this. Okay, so what you're going to see here is these node labels. In just a second here, you're going to see a lot more node labels show up. Okay, check that out. That's pretty sweet. We got a whole bunch more. So let's just quickly look at this graph. Match N, return N. Okay, let's blow this up. It's thinking. Oh, I want it in graph mode. Okay, check that out. Now I've got nodes that have different colors on them. And if you want to change colors, go spend some time looking at how browser works. It makes it easier to see. But I can see that I've got things as red labels. I've got administrative areas as pink. Okay, that's all cool. That looks good. So let's do a little bit of data science here. How many Obamas are in the graph? You remember I said that the subject verb object thing was going to result in a lot of duplicates. So we're going to use, let's just talk about what this query means here. This was similar to that query that I showed in the slides. I'm going to match a node. That node, I'm giving the variable name N. I'm going to return the name N, and I want that name to contain Obama. And then I'm going to return all distinct versions of that. So let's go. Okay, I've got a lot of instances of Obama showing up here. Michelle Obama, President Barack Obama, Barack Obama, Barack Hussein Obama. Obviously, we've got a problem here with entity resolution, or entity disambiguation. Okay, that's something we're going to have to think about how to deal with. Now, it's your turn. I am going to ask you to figure out, where was Barack Obama born? Now, just to give you some context here, I am going to, I could do match node, and let's just make this simple. We're going to say Barack. Let's actually grab that phonetic spelling. Is that down here somewhere? Yeah, because we know that this was the central node in the graph. Okay, so match node. Now, this is just a different way of saying this. Name. Okay, this is just kind of like a dictionary. They call it a map when you're talking Neo4j. Now, we could have relationships here. Okay, and relationships usually start with a colon. Okay, so I could look at this list here, and maybe I'm going to come up with something here. I'm just going to, just for the sake of showing you some Cipher, I'm going to say that that node is going through a relationship. And now I've given an arrow. So to give that arrow, I'm using the greater than sign, and it makes it a nice little, looks more like an arrow. And we're going to just match some other node, which we're going to call M for the sake of just argument. And I'm going to return N and M. Okay. And so what I see, I've got nothing here. That's interesting. Okay. Just that'll give you some helpful starting cipher for trying to figure out where Barack Obama was born. So take a second and try to figure this out and post your answers in chat. There's a few different ways that you can do this, by the way. While you do this, I'm closing my curtain because right now the sun is just hitting me in the face. By the way, you have to find it with the graph, not your own personal knowledge. Okay, we have somebody talking about the relationship of born. This is a really good path to be going on, but I will tell you, we are getting the lemmas. Oh, it was pointed out I have an extra. This is one of the joys of giving live demos, is I actually put an extra tick here. I have too many quotes, so let's just see what happens if I run that. Ooh. Oh, interesting. Yeah, but thank you, Ananth. Okay, let's go over some solutions here. Here's one way that we could do it. Let's say that I cared about, okay, I'm looking at my node of Obama. I could get everything that's connected. And in fact, what you see here with this relationship, and those of you who are in SQL, this is one of the absolute most powerful things about Cipher. What this says here is I'm going to get all nodes called P that are 1 to 5 hops from Barack Obama. That 5 is just arbitrary. You could put anything in there. Now, if you think about that, think about the SQL query. If I tried to do a join after a join after a join, I have to do a lot of joins here, really unpleasant joins, to get to get all the answers here. So this is one of the cool things about Cipher. Because it treats relationships like those first-class citizens, we can do that. That's like one of my absolute favorite things about Cipher. Okay, so I am going to say 1 to 5 hops, Obama connected to P, where P has a label, a node label of country or administrative area or continent or place, and let's return both Obama and that place. Okay, you can see here, let me close this guy so we're not so memory intensive. I have a lot of places here, and obviously some of them are wrong. I look at things like Russia and Cuba and Ukraine. Obviously, those are incorrect. So let's look at another way of doing this. And this was somebody earlier was getting at this. Okay, I'm just copying these from the answer file here. And again, that answer file, I will be merging that into the repository later today. So just stay tuned. It's probably not going to be immediately after, but sometime today. Okay, here I am now specifying my relation type. I want my relation type to either be B or bear. Remember, we are using the lemmas here. And so bear is the lemma of born. So let's see what happens here. And again, I'm specifying places as my labels. Okay, now I see here's bear. Okay, so Obama was born in Honolulu. He B, United States. Okay, so maybe not here. Maybe B is not the correct verb here. But yeah, so Honolulu, very cool. All right, so let's cruise along here a touch. Let's go back into our query file. Okay, I'm just going to cruise through this one really fast, just in the interest of time. There are duplicates, as we talked about in this graph, and I'm going to show you just quickly how we're going to query it. This will be in the answer file. What I'm doing is I'm matching nodes. I'm matching their labels because I don't want to say, Barack Obama as a thing is the same thing as Barack Obama as a person. And I'm going to collect them, meaning I'm assembling a list. I'm creating a list. And I'm going to say that the size of that list is greater than 1. Okay, so let's see what this does. Oh gosh. Okay, so I get lots of Barack Hussein Obama II. Ugh, the size, I have 20 of those. I have 8 things called district. Okay, we have to dedupe even more. How are we going to do that? Well, there is a query here that will show you drop duplicates. This is lines 27 through 30. So let's copy and paste that into browser here. And what I see is that for each of these things that have more than 1, I am going to delete it. So my command detach delete, detach it from the graph and delete it. Okay, and this is what list comprehension looks like in Cipher. So let's just run that. Going to get rid of some nodes here. Watch over here. We deleted 205 nodes and 265 relationships. Okay, so that's done with. Okay. If you're curious, we can get the cosine similarity between 2 nodes. Here I'm doing it between word vectors. Cosine similarity is a built-in function in the alpha level of Graph Data Science Library, or GDS. I'm not going to do that right now. Here's a quick little way that we might think of disambiguating or entity resolving some of our nodes. This is the Levenshtein distance. And what Levenshtein distance looks at is how many characters different are 2 things. So if 2 strings are exactly identical, their distance is 0. If they're 1 character off, the Levenshtein distance is 1. Okay, so smaller is better in this case. So I didn't order Barack Obama is identical to Barack Obama, makes sense. So this is just kind of a way that you might try and get at, well, if I have a small Levenshtein distance, then maybe those things are the same. Okay, now let's go run some actual data science code. Okay, we are going to, this is in our Collab. Remember, we populated this directly from the repo, and we need to install one package that's not automatically within Collab, and that's Python. So we're just going to, that bang pip install, that's just telling it to run that like from the command line. it says, uh-oh, it was not authored by Google. Oh, shoot, run it anyway. Okay, so what you're going to see here in just a second is we're going to populate, we're going to pip install that package. Once it's done running, cool. Now we've got all of our imports here. Okay, so let's run that. Okay, we've imported. Now, here's where we're going to have to populate some stuff. If you are running on your own machine, this is going to look a little different, but this is the general syntax for how to connect to a running instance, a running database. So we're going to need this URI and we're going to need our password. We're going to get that from our sandbox here. So let's drop down here and our connection details. So first, remember, here's our IP address. Okay, so we're going to go put that into our notebook right here. Okay, and then we need the password. Let's go get the password. Password is right here. Let's copy that. We're going to paste that in there. Okay, cool. Now we're using Python Neo to make our connection. It's using this graph class to do it. All right, let's run that. All right, we got no errors. Yay, that means we're connected. Cool. All right, let's just do a little bit more entity disambiguation just for fun here. And what I'm going to hypothesize here, I'm going to hypothesize that if I have two nodes that are the same thing, such as the phonetic spelling of Obama and Barack Hussein Obama II, we should get a strong overlap in the relationships between those two things. So my first one here, I'm saying, give me every node. Oh, by the way, look at that. I can run Cipher from Python. How cool. Think about some of your SQL connectors, your SQL packages. Same idea. We can do the same thing with Cipher. Okay, so I've got my node, Barack Obama. I'm going to return the number of distinct nodes that it's connected to. Let's do that. So what nodes? Okay. That version of President Barack Obama has one node of the Affordable Care Act. Now let's do it for the phonetic spelling of Obama. Okay, 115 nodes, because that's kind of the central node, so I guess that makes sense. Now the question is, do I see the Affordable Care Act in these 115 nodes? So I'm going to just do a set overlap between the two. And I get 100% because the answer is yes, they both overlap. Now, obviously, if I did this the other way around, I'm going to get a horrible overlap because, 115, are all 115 in that one? No, they're not. Okay. Now we're going to do some machine learning. Oh, thank God. In order to do that, we're just going to do basic node classification. This is a really cheesy problem. I'm going to tell you right now. It's very, very, very made up. Okay, what we're going to do is we're going to create some properties. We're going to try and identify whether a thing is a person, a place, a thing, or an unknown. Okay, so just for the sake of time, I'm going to copy and paste all of these commands in here. So that's lines 46 through 75. Now, what I have done is I said that the node labels are in a list here. And these are completely arbitrary. I just kind of manually said, okay, I could have a person, I could have an educational organization, I have a corporation. Okay, so this is completely superficial and made up. All right, but let's do it. So I'm setting node properties called PPTU thing, PPTU person, blah, blah, blah. And those are going to be used for our classification problem. So I'm copying those and I'm going to paste them into browser just to get this done here. Okay, so we see it's running multiple commands. Return node. Return can only be used at the end of a query. Oh, that's cute. One of the joys of live. Oh. Yeah, okay. So I didn't have a semicolon there. That's great. Let's do all three of these. I'll fix that in the repo. Okay, so we're going to run these slightly separately. Okay, cool. All right, so we've got that run. Let's now, we're going to create now a data frame. That's one of the things I really like about Py2Neo is it creates data frames really easily. And you kind of have to scroll over to see how it happens here. I have just this to data frame method, which is really handy. Let's run this. And you see I get a data frame. Okay. Now, here's something we have not yet done. We're going to need to rerun this because you see, I have this thing here, N2V all nodes is 0. Okay, we have not populated our graph embeddings yet, so we're going to need to do that. All right, so let's come back to our Cipher here. Now, in order to populate these things, we're going to have to create an in-memory graph. What that means, this is a GDS thing, and GDS has this is a wonderful change from how we used to do this in the old graph algorithms library days. That's an old library, it's no longer supported. GDS is what we do now. And an in-memory graph is essentially us taking, okay, I care about this portion of my graph. I don't care about the other portion, but this portion I'm going to put into a special format that GDS can then run its functions on. Now, there's an art to this, but let me walk you through what this means. Okay, I am creating a graph and it's going to be called all nodes. Okay, now in general, you do not actually want to do every single node and every single relationship. And the reason for that is, especially as your graph gets big, this is going to become cumbersome. But if you think about it, like let's say I wanted to calculate the importance of a node through like PageRank. Okay, maybe it's a person connected to cities, which are the most important people in the Senate or in politics. Well, if I were to run like PageRank on that, it doesn't make sense for me to say the importance of a person relative to the importance of, the different political organizations. So I don't want to actually specify all nodes here. This is really just, a simple made up example here, but we're going to create this graph. Okay. In-memory graph here. And what it's saying is I have two dictionaries here. One of them is called all nodes, and it's got the label of node. So everything that has the label of node, which if you recall is everything in the graph, is going to be in this graph. And then I'm going to bring in some properties here. I'm bringing it this is just for demonstration purposes. I'm bringing in word to vector embeddings. That's the property word vec for each of our nodes. I'm bringing in all relationships too. Again, not a great idea when you're doing this for real, but that's just saying all relationships. And then you see I'm specifying an orientation of undirected. The reason here, our graph actually is directed, but a lot of the GDS algorithms prefer undirected. So what's going to happen here is it's going to actually create an additional relationship. So you'll see arrows going one way and the other way. We should see doubling the amount of relationships here, which we do. Okay, cool. So now we have our in-memory graph. So let's go and we're going to start doing some stuff with it. Let's look at creating node to vec embeddings. Okay, so let's copy and paste lines 91 to 93 in the browser. Okay, here we are. So I'm telling it, node to vec is at the beta level presently. We're going to take our in-memory graph called all nodes, and we're going to create an embedding dimension of 10. Now, there's all kinds of hyperparameters that I could be putting in here. I'm not dealing with them today. Hyperparameter optimization, we're not optimizing absolutely anything. So when you do this for real, you definitely want to spend time optimizing. Okay, so when I say stream, what this is going to do is it's just going to show this to the screen here. So let's run this. One of the things I want to point out is this thing called GDS util as node ID. Okay. In GDS, things are stored just by ID numbers. We can convert them back using this function. So I'm converting it back and returning the name of that node. And it's being returned as a variable called name. Sorry that I seem to be losing my voice here. Okay, here they are. So here's our graph embeddings, just created for us, super simple. If any of you have ever tried to create these graph embeddings using other Python functions available on the internet, other Python code, this takes absolutely forever. Okay, I highly recommend anything you can do in Cipher, you do. Okay, anything that you can do on Neo4j, by all means do it before you actually suck it into Python. It's much more efficient. These vectors create themselves really quickly. Okay, so we've looked at what they look like, but I actually want to write them to the graph because that's how we're going to use them in our machine learning. Okay, so this is lines 96 to 101. Okay, I'm going to paste that in here. Okay, so in this case, we're actually writing to the graph to our actual nodes. I'm going to create a property that's called N2V, all nodes. That means node to vec for the all nodes graph. So let's run that. Okay, it'll take a second. All right, so it's done. Let's go see what that looks like over here. We're going to rerun this to data frame query. And ideally what we see is that this final column, I have vectors here. Excellent. Okay, cool. Now what you'll also see is I have these columns, whether I've identified the thing to be a person, a place, a thing, an unknown. And you'll see that I have things that can be multiple things. The United States is both identified as a place and let's see, a place and an administrative area and a thing. Okay, so that can happen here, and that's fine. We're gonna still do some binary classification on it. If we were truly doing this for real, though, you recognize that as a multi-class problem. We're not actually going to do it that way today because this is such a small graph. We know we're going to get horrible results. This really is just for demonstration purposes. Okay, now I got to get this in the style of scikit-learn. We're going to be using a support vector classifier from the support vector machine portion of scikit-learn. So let's just do that. Okay, so we're just getting things in the correct format for that. One thing you'll notice is that, if I have no description for my node, remember those descriptions are the things that we create word vectors off of. I will have no word vector. So I'm actually just creating a list of zeros here for that word vector. Okay, so we've now gotten this in a way that scikit-learn actually likes. Okay, I'm just creating a function here that's going to handle the model. Here's the actual model. What you're going to find here in a minute is that we have a significant class imbalance when we do this. You can add something here called class weight, I think is the name of the special hyperparameter for SVC. I'm not going to do that right now. Let's just run this really fast. Okay, so let's look at my word vectors. I'm going to look at the accuracy of what happens if I use my word vectors associated with my people. Do I identify somebody as a person or not? And I get an accuracy of, roughly 86%, which is really not bad if you think about it, especially when I'm dealing with such a class imbalance. I have, 119 cases of person and 538 cases of not person. Okay, but let's compare that now to our graph embeddings. Okay, so let's run this. Okay, I got 83%. That's actually really close, and I only have a 10-dimensional vector. So that's kind of cool. We can run this for all the other ones, and that's great. I want to get through our next example here for the sake of time. Now, like I said, we totally did not tune our hyperparameters on the graph embeddings, on the word vectors, on the models, and we're already getting, accuracies in the 80%. And actually, if you run some of these other ones, I think it's the places, I think you actually even get into the 90%. And that's with my graph. So that's pretty darn cool. If I did that with my word vectors, I'm getting, 93% again. So very cool. We're going to create now another sandbox. I'm going to go through the Wikidata stuff just really fast. So let's create, you can't create two sandboxes of the same type. So instead, we're going to create a blank sandbox for graph data science. We're going to launch it. Okay, these take a little longer to spin up. So while it's doing it, let's create our new Collab notebook. Remember, I'm going to create new Google Collaboratory. And I'm sorry I'm going through this so fast. I have a lot of content that I want to cover today. We're going to go File, Open Notebook from GitHub. Let's put in our URL, github.com, CJ. Let's just copy it over. It's the smarter way to do it so we don't have typos here. Okay, let's go back into just the repo so I get the actual URL. Copy that, paste that in here, search for it, and we're going to actually look at notebook number 4. You can walk through how number 3 works. That's just populating the graph with Wikidata. I do want to point out when we do that, let's go into the notebooks directory. I don't have time to go through all the slides on that. Again, the slides are in the repo that talk you through this, and the notebooks are pretty commented. And the one thing down a touch, we're again entities via spacing, rid of dates, I'm cleaning text. I've got a whole bunch of named entities here. I've got to get my P and Q values for them. This is showing you how to make the connection to Wikidata. What I want to get at, though, here's my Q values associated with all those named entities. But the thing is how to get the verbs. I had to manually go in and specify these things. If you search for Wikidata, you can get these P codes. I just picked a bunch that I thought were interesting. You'll need to manually do this for yourself. Okay, so that's one of the drawbacks of this approach. Okay, so, but we're actually going to go into Notebook 4 where we're actually going to do some data science here. Okay. In this case, we're using the official driver for Neo4j. Again, go to my Medium page. You'll find out how to do that. But first, we actually need to populate that graph. So if I go back into the repo, and in this case, I'm going to go to my Cipher Queries, okay, my starting queries, and I'm going to scroll down here. The last line here is how we're going to import the JSON. Okay, it's just like we did before. This graph is pre-built based on notebook number 3. Oops, I need to actually open in browser now my correct database. Don't want to write this over the original database. That's going to create confusion. Okay, and like I said, these are slightly larger instances, these blank graph data science ones. And so what you want to do is just give it a little bit more time while it spins that up. Okay. Da-da-da. You know what, while it's doing that, let's kick off some stuff here. We'll pip install the Neo4j package. That'll take a second. Okay, we're gonna wait for that to be done, and we're gonna do all of our imports. If you know me, like I import everything and stuff that I probably don't need, but you know, it's just how I roll. Okay, I'm creating this connection class here. Again, this is described in some of my blog posts. Okay, now we're gonna get to the place where we're gonna make a connection. Let's see if our graph is actually done. Oops. Oh, we haven't actually populated it. We were waiting for the browser. Huh. Okay, now we're actually going to populate it using that APOC import function in the starting queries. Okay, and this is going to take it a second. We can click on the database button over here and see it happen if we want. Any reason you are not using DBpedia Spotlight? Wikidata seems to be an industry standard, but it would remove the hassle. Yeah, this is just for demonstration purposes. You could use whatever you want. This is, you know, this is just for fun. Just kind of walking you through one way that it could be done. Let's look at this graph really quick. Okay. So it's bouncing all around here as it assembles the actual visualization, but you know, it looks cool to me. I recognize that, trust me. Let's see how many nodes and edges. I've got 1,325 nodes. I've got 1,638 edges. Okay, cool. We're going to get this into a format that will work for our machine learning. So we're going to go into method 2 queries now. Okay, I'm going to drop duplicates using that same bit that I used in method 1, just cruising through here because we've got about 15 minutes left. Okay, so just trust, there's not going to be many of those. There's 6 of them, okay, just because of how we created this graph. Now, here I have, just from how I created the data set, I need to convert, I'm using lines 16 and 17. I want to create those new node labels. It's slightly different based on the Python that I wrote here. So, oops, I need a couple different queries. So lines 20 through 22 are what I'm running right now. Okay, so let's run that. Okay, cool. So I've got a whole bunch of new node labels right now. It's kind of just like we had before. You'll notice, though, that Barack Obama was my search query, but look, United States of America is way more prevalent in the graph, so that's kind of neat. Okay, now let's just, this is an exercise I was going to give you, but for the sake of time, I'm just going to show you how to run this one. This is, again, the where was Barack Obama born query. Let's just go do that really quick. You'll see it's actually much easier with the Wikidata data, because I have an edge that's called place to birth because I told it to make that. Okay, I have the place, the hospital, I have Honolulu, and then I have Kenya. Okay, obviously that was a debatable thing in the news, but it came up in our graph here. Again, your subject matter expert needs to be involved in this. Okay, so now we're going to do kind of something similar to what we did before. Find a lot of places to do classification to try and identify whether something place. Now, again, I've manually added these things here, this list of things that could be places. You know, if you're doing different graphs, you're going to have to come up with your list yourself. Again, that's the work of a subject matter expert. Okay, so we're setting a property for my nodes that are in this list where my place is equal to 1, just like we did before. And then anything that doesn't have that, where my place is null, I'm going to set to is place is 0. So 1 means it's a place, 0 means it's not a place. Oops. Okay. What you'll find is you're going to get about, you have some class imbalance here. You have about 413 places and 906 non-places. But again, let's go and create our graph. We're going to use all of our nodes. Again, remember, that's not a great idea, but this is just for demonstration purposes. So our in-memory graph through GDS is what's going to allow us to use GDS functions on this graph. Okay, and again, I did this as an undirected graph, so you see my relationship count is double. Okay, now we're going to write out some embeddings to that graph. Okay, there's actually an error here. My graph name is called all nodes, not places. So we're going to have to be careful of that. So we'll call this all nodes. Okay. Cool. I have written my embeddings, again, 10-dimensional embeddings. I'm calling this N to V for node to Vect, because just for fun, let's create vectors with a different type of embedding called FastRP. Okay, it's just a different way of doing a skipgram around the graph. We're just going to see if that does anything for us. Again, I need to replace my graph name with all nodes. Okay, so I've got some more embeddings, and now we're going to do some data science on these things. So first off, we need to establish our connection, which we're going to need the Bolt IP address for, so we're going to throw that in here. I'm going to need my password of my sandbox. Here it is. one of the things I always do is grab the wrong sandbox and password and then be like, wait a second, why do I not have the right number of nodes? I just counted nodes just to make sure that I was established to the graph and it was populated. Okay, we're going to just look at TSNA embeddings. Again, let's look at first node to vector embeddings. So what I'm doing here is I'm creating a data frame with that above create TSNA plot function. It's a little more complicated to do it with the Neo4 official driver than it is with the community driver Py2Neo, but I show you up here how to do it. It's basically, you know, going through this dictionary here when you do your query. Okay, so that's not great. I see that my red and my blue dots are overlapping. It's not what I want to see. But again, I don't have a very big graph and I don't have my embeddings optimized. Let's do this for FastRP really quick. Okay, so it's pulling down those embeddings. It's creating a two-dimensional dimensionality reduction. Okay, still not great, but this isn't really surprising because of the size of the graph and everything. But let's do some modeling on it. We're going to try to do just binary classification of is it a place or is it not a place. This is going to look pretty much exactly like we had before. I'm getting things in a right format. I'm creating a model. I'm actually, I didn't mention this before, but I'm doing a k-folds validation of 5-fold. So just trying to make my model a little better here. Let's get those functions loaded in. And now we're going to run it. So I have my query string. I'm creating data frames for my models. Let's see what those look like. Okay, so I've got my node to Vect embeddings, and I've got my FastRP embeddings. Okay, I've got my category here. 0 means non-place, 1 means place. Let's run it. Let's see what happens when I run my node to Vect embeddings. Okay, I've got a 72% accuracy. Again, I have that node, that class imbalance problem. It's not great. It's not horrible, but this is just for you to see how you would do it. Let's try it now with the FastRP vectors. Okay, 76%, nothing to really write home about, but I'm higher than 50% means I'm automatically doing better than random guessing. So I guess that's good. Okay, so some observations about this. Let's, we didn't tune anything. Let's just look at, you know, what if I gave it some different things in the graph? Can I predict correct things? Do they make sense? Sometimes I do, sometimes they don't. The city of the United States, it came back that it was not a place. Let's try this for Illinois. The state of Illinois. Oh, predicted class of 1. So it did get that it was a place. So that's slightly reassuring. Okay, so what would we want to do from here? First off, these graphs are small. Okay, they're really small. It's not the greatest demonstration, but again, it's just for time's sake. We want to add more data to the graph whenever we can. It's good for the graph and it's good for the ML. You also obviously want to optimize these embeddings. That is an art. Those of you who've done traditional ML know that's an art. Same thing when you're doing graph embeddings. Another one, I only showed 2 of the embedding methods that we have built in GDS. There's another one called GraphSage. It's super sophisticated. But what GraphSage can do is it can take into account the node properties when it does the random walk. So, you know, it can make a much more sophisticated embedding because of that. I strongly recommend you read about those 3 embedding types in the GDS documentation. And then there's another thing that you can do here if you want to get a lot more sophisticated. Within GDS, they've started adding some machine learning functionality. And in particular, it will do node classification and link prediction for you, built-in things to do that. Uses logistic regression. I was using support vector machines. Lots of hyperparameters to tune. It can do some of that for you. I'm not showing it right now because A, we're running low on time, and B, because those things really shine when you have larger graphs than what we're dealing with today. But if you're interested, great things to take a look at. Again, check out the docs on that. And there's also developer guides showing how to use each of those. Okay, in the remaining 4 minutes, let's go back to our slides. All right, here we are. All right, where do we go from here? We've already talked about some of this, but I want to start by reminding you of the 2 key concepts that we talked about at the beginning of this workshop. Again, these are the 2 things that if you took nothing else away from today, these are the 2 that you should take away. First off, as you saw today, there is no proverbial silver bullet associated with NLP. Remember the whole reliance on subject matter experts, the fact that text is dirty and really hard to deal with. These things are all stuff that you got to consider if you're doing like a huge corpus of data. You know, maybe you have many, many, many documents. Just be warned, NLP is hard, okay? Secondly, the quality of what you get in is based on the quality of what you put, or the quality of what you get out is based on the quality of what you put in. So I showed you some really small graphs. Look at making those graphs bigger. Look at having those relationship types be more instructive, adding properties to your nodes, and really refining what would go into an in-memory graph. Not all nodes and all relationships, but get specific. You know, I care about people who were who wrote this legislation. I care about rock stars who were creating albums in, you know, rock stars who are collaborating with other rock stars in bands that existed in the 1970s, whatever. Get specific. Okay, I said adding nodes to the graph, embedding optimization techniques, adding data, word vectors from the text descriptions. Maybe you could use those as node properties within like GraphSage or something like that. People always ask, can I do deep learning on graphs? The answer is absolutely, resoundingly yes. Some of the GDS algorithms have graph neural networks under the hood, but you know, you could take those embeddings out and put them in your own like TensorFlow or PyTorch functionality. There's all kinds of great deep learning things out there and more every day coming up for analyzing graphs. So that's cool. Problems we could solve: community and cluster detection, node classification, and link prediction. Those 2 bullets, those are all built into the GDS library right now. Graph to graph classification, that's a very cool area. It's way beyond the scope of today. But think about, you know, molecules are graphs. I want to know, is this molecule represented a graph similar to this other molecule represented as a graph? Unstructured text actually is a graph. Remember, I was showing those arrows with words pointing to other words. That's a graph. You could create an actual NLP engine of your own just with graphs. And then question answering systems like we talked about before. So we are at time. It is 30 seconds before the end of class. So I just want to say thank you. I love teaching this subject. I love hearing from people from around the world, just about what kind of problems you have, what kind of graph problems. How do you know you have a graphy problem to begin with? Here's a spoiler alert. If you have many joins in a SQL query, be thinking graphs. Okay, that's the biggest hint that you have a graph problem. Again, reach out to me on Twitter. That's my Twitter handle at the bottom. Check out some of my articles on Medium. And just thank you. Thank you for attending. It's been really great.